So our next speaker is Dirk Pattinson from London.
So, also I want to say thanks for the invitation. So, what I want to do is I also want to give you a perspective on coalgebras, but not from the point of view of computation, but from the point of reasoning. And I feel sort of slightly guilty because my truthful intention is to use you as guinea pigs to sort of learn more about essentially how this can be applied to quantum phenomena, and I'll make a few remarks later on. So the content of this talk, I should say, is based on joint work with these people here. So when it comes to reasoning, I want to give you sort of an introduction by example. So we probably all know these two. The gentleman in the middle is Henry Carey. What makes the set interesting is that there's been speculation that Henry Carey is actually an illegitimate son of Henry VIII. And I want to sort of represent this information. So what do we know about the situation? So we know that Mary Boleyn was Henry's mistress. So I think Mary was Catherine of Aragon's lady-in-waiting at some point. And to make the whole example more interesting, let's suppose that the not yet invented discipline of quantitative late medieval history tells us that there's a 20% chance that Henry Carey is actually a son of Henry VIII. Okay, so we have some quantitative uncertainty. So what's a good model? So we only have probabilistic information about the offspring of Henry. So this is Elizabeth I, this is Queen Mary, I believe. So you see that Henry appears in some of the possible sets of children. So the lady here is Henry Carey's sister, who's also rumored to be an illegitimate child of Henry VIII. So the notion of model that we have is probability distributions. So I'm thankfully using the same symbol over sets of individuals that we think of as being the children. So let's assume that we've got a certain degree of certainty when it comes to amorous affairs. So we know that Henry had amorous affairs with a number of people. So here's Mary again. So that means that the models are relations. From every point, to every point, I assign the set of individuals with whom sort of the individual on the left-hand side have an affair. And I can combine these two facets by simply taking Cartesian products. So this is sort of the setup. So of course we may also think of this as a dynamical system, which I don't want to do for the purpose of this talk, but it's of course an interesting question. So it could be probabilistic, it could be quantum, whatever, but let's think of it as static. So we're looking for a logical language that allows us to speak about these things. So we want propositional variables so that we can express concepts like being a king. On the other hand, if we want to talk about people like Henry VIII, it doesn't make sense to model that as a property that a person can either have or not have. So we want a set n of individual variables that allows us to identify the certain individuals in the model, and we want a set of operators like has had an affair with, and we have a language that contains sort of the Boolean connectives. We've got these propositional and individual variables. We've got modal operators, which can be sort of n-ary, and we've got a special feature that allows us to say things like Henry is a king, so this is an individual variable. This is a concept which can be sort of atomic or compound. So this is essentially the linguistic means that we have to say something about properties of certain individuals. So let's say we want a modality that says has had an affair with, and we want another modality saying that the probability is at least p that someone with a certain property is a child. So the models are triples, so we have a set of individuals, we have a transition function that gives us the probabilities about on offspring and sort of the affairs, and we have a valuation that assigns a meaning to each variable, to each individual, where we require that individuals are evaluated as singleton sets. And once we're there, it's quite easy to give the semantics to these operators. So an individual W satisfies diamond A. So the reading is that W has had an affair with somebody satisfying property A. So we push it through this function, we look at the right component, and we say yes if somebody with property A is in this set. Similarly for the other one, we just look at the first component, we say that sort of the probability distribution must be such that it assigns property at least P to the set of all offspring, if you like, that have at least one member from A, and as announced, the so-called satisfaction operators, what they do is they just move the evaluation context, essentially, so this means that individual I satisfies property A, which is independent of the current state. What happens is that the evaluation context, so everything that's being asserted is that the point that is named I in the model indeed has property A. So this is the setting in which I want to do reasoning, but of course I don't only want to reason about the tutors, which would be probably interesting, but slightly boring in the long run. So I want to generalize these models to coalgebras, where here I have a set of structured successors. So I take a functor. So what I'm saying here is essentially you can think of things happening in set. You can also think about other categories. So the modal operators get interpreted in a characteristic way. So I push my state through the structure map, or the transition function if you like, and then I ask that sort of the set of structured successors, so the element that I get, so which is pairs of distributions and relational successors in this case, has a certain property, which means that I can sort of abstract that into a function that takes a property on states, which is A, and turns it into a property of structured successors. And this means that essentially I can roll my own. I can sort of apply this setting in quite a large number of examples. So here's the setup. So I have a collection of operators. I have a specification, if you like, of the situation I'm interested in, and these are the models that I want to look at. So I have states, and I have structured successors or observations. And to each operator of the language, I have to associate a meaning in the sense that it takes a property in states and gives me sort of an induced property on successors. And if we want to use that for knowledge representation purposes, we want to do reasoning, so we're interested in questions like consistency, satisfiability, etc., etc. So the most general formulation of this question is that we start with a usually finite set of formulas that specifies the knowledge that we have about a specific application domain. So everything we know about the tutors, and we take a single formula that we think of being a hypothesis, and we want to answer the question, is this hypothesis A, consistent with respect to this background knowledge? In other words, is there a model such that every point satisfies all the formulas in here, and at least one point satisfies A? And we're interested in decidability, complexity, algorithmic issues. So we get lots of examples, essentially by varying the ingredients. So what I've been thinking about is to what extent one can also vary the category in which this happens. So essentially we could take, instead of sets, we could take sort of a pre-sheaf topos that describes quantum states that we then manipulate in a suitable way. So that's not something I can say anything about, it's more a question for the audience. And I want to give you sort of a brief description of essentially the reasoning process. So what I want to use is I want to use tableaus and their sort of a basic ingredient, which is obviously a rule. So here I'm considering the case of just unary operators, and this is how the rules look like. So if I have a point in the model that satisfies all these properties, to satisfy all these properties, we should read it the other way around, we have to satisfy the properties in either of the sigmas here, which are the conclusions, and they just consist of material that is sort of copied from the premise but possibly negated, which is what the plus minus should insinuate. And we have sort of a basic coherence condition that I don't want to dwell on, but if we take a set of formulas of this form, then if the interpretation of that is non-empty, then the interpretation of at least one of the conclusions must be empty. So I always need to find a rule with that property, which essentially mediates between sets of successors, and which is the interpretation of gamma, and sets of states. And we know these rule sets for a large number of examples. So there are essentially three variations to the basic theme, depending on the features that I want to support. So let's forget about individual variables and satisfaction operators. So the first correspondence that one sets up under these coherence conditions that I've mentioned is that unsatisfiability corresponds to the existence of a closed tableau, where we also need the standard rules for propositional logic here. And essentially the proof idea is to construct satisfying models in the case that no closed tableau exists, step by step, employing sort of the basic coherence condition at every step in the model construction. You can implement this on an alternating Turing machine if you like, and obtain polynomial space as an upper complexity bound. So let's add some global assumptions or background knowledge, but still not quite individual variables. So then we have sort of a a finite set of formulas that we want to be sort of universally validated in the model, we're interested in the same correspondence, but we have to adapt the calculus in a hopefully intuitive way. Namely, what we need to do is we need to sort of add the background knowledge to every point intuitively. So what this rule does is it performs a state jump. It goes from successors to states. So in order to satisfy this successor property, I need to create a state. This state needs to validate all the global assumptions, so they're just added to each conclusion. So, which means that essentially we can create loops when we analyze these tableaus, which corresponds to complexity jump from polynomial space to exponential time, which is sort of a type bound for many instantiations. So, and the question is, what do we do if we also want to reason about individuals? So, if we're interested in complexity bounds, we could say it's very easy indeed. So everything is finite. We only see finitely many individuals. So in the first round, we just guess for each individual or for each nominal, we guess a certain set of formulas, which are sort of subformulas of the background knowledge and the hypothesis that we think that this individual could satisfy. And then we just sort of use sort of the method I've outlined previously. So we just ignore the nominals and the satisfaction operators, and whenever we find one, we replace it by true if we think, so if we've already guessed that this holds at point I. And what we additionally need to do is we need to check that essentially our guesses, so these are sort of formulas or sets of formulas that need to be realized at individual states if we want to construct a model, is actually consistent. So if you do the maths, then essentially the guessing takes only exponentially many steps. Each step can be performed in exponential time, so we still get an x time bound. But guessing seems to be too heavy-handed. So what we're really after is sort of an algorithm that does this sort of in a cleverer way. And essentially, it's very hard to describe this algorithm in terms of the analysis of a particular calculus. It's much easier to describe that in terms of propagation. So let's assume that we want to satisfy these two formulas. So we need to create one successor that satisfies this formula, which means that I has to satisfy P. So unfolding that, we create a successor that satisfies the formula here in parentheses, which is a disjunction, so we can satisfy the left-hand side, which means that again we need to create a successor that satisfies at IQ. So here it is. But for that to make sense, of course, P and Q have to be satisfiable at point I. So essentially what we do is we propagate this and then check for the joint satisfiability of the fact that at point I have both P and Q. So for bureaucratic reasons, essentially because it could be that P and Q are sort of compound formulas, one has to drag them around. So for bureaucratic reasons, I have to add these two. So here I have a setup where I've done no guessing. Also, I haven't unfolded the possibly complicated bit here, which means that I can get sort of an answer before having constructed a full proof tree. So this is to see that it also works the other way around. So here I've got something that's very complicated. This tells me that I need to create a successor such that at point I bottom holds, but if at point I we require that bottom holds, we can propagate this. So we mark this as sort of incomplete information because more things could be sort of required to hold at this point. But this, the satisfiability of this can already be challenged, and we can declare unsatisfiability of the root. So what I want to point out is that in both examples we could announce satisfiable or unsatisfiable without having to unfold things completely. So we have sort of a purely sort of tableau style syntactic decision procedure that sort of leaves room for the usual heuristics. And it seems that this also is an algorithm that hasn't been known in the literature before. And thanks for your attention. That's it. So the question that I'd sort of like to ask is, to what sense does something like this make sense in a quantum world? Okay, thanks for your attention.
Well, we are behind schedule, but I guess there is time for one or two questions. Okay.
So just to clarify, the bound is a known bound, but your algorithm is different. You haven't improved the bound, but it feels heuristically that your algorithm might do better in some cases because it's doing this kind of lazy evaluation. Is that
essentially the bound falls out very, very easily. So essentially by just translating the problem to exponentially many satisfiability problems for the case without individuals. So I will claim this as a result.
But the algorithm isn't doing better than that bound in the worst case.
In the worst case it isn't.
But you feel that there may be, well, I mean, I suppose that is the general question, which is that one sees these X time and even P space. I mean, from a certain point of view, that looks bad. But of course, in this game, it's maybe you want to make a comment on that because you know what it means in practice, as it were, to have logics with these bounds.
In my opinion, yes. I mean, there are sort of a number of examples that sort of work purely in terms of relational semantics. So you think of medical ontologies which are being classified using, essentially these methods. So essentially, what we can do on top of that is things like probabilities or notions of, I don't know, conditional implication or multi-agent systems without going to sort of higher complexity bounds. Also, so if you look at an actual implementation, what you see is that the algorithms that are implemented are in complexity optimal. So usually satisfiability is implemented using sort of backtracking, which gives a worst case bound of non-deterministic exponential time. So at least here we've got something that meets the optimal bound.
Okay, I think we must move on to the next speaker, so let's thank you again.